This lecture or web note is maybe one of the most beautiful ones on function analysis. This is where we discuss the fundamental or the core theorems of function analysis, and they are all related to the behavior and the properties of linear operators defined on normal vector spaces or Banach spaces. The main ones, as we know, are the uniform boundedness principle, the Banach-Steinhaus theorem, the open mapping theorem, the closed graph theorem, and the last one is the classical Banach theorem, which we will not discuss in this one, but we'll discuss in another lecture, which is also, by the way, about linear operators, except that it's related to linear operators where the target sets are what we call linear functionals. Okay? So let us start by putting the setting. Let's, as usual, let U and V be two normed vector spaces, two normed vector spaces. We know that L of UV stands for linear operators from U into V. And finally, BUV are the bounded linear operators from U into V. Okay? So we'll consider, of course, the norm operator as defined in a previous lecture. And we know that if V is a Banach space, then BUV is a Banach space. So we have the following theorem. So the first theorem from the list, the main ones. This is known as the uniform boundedness principle, or the principle of uniform boundedness. It doesn't matter how you call it. Uniform boundedness principle. And it is stated as, let U be Banach. So we assume that U is a Banach space, and V is a normed vector space, normed vector B, a normed vector space. Let A let A be a family of bounded linear operators. So here this is a subset of BUV, non-empty. So a collection or a family of, so we assume that pointwise the family is bounded. So we assume that A belongs to the family A is bounded in V. Okay, so then the family A is bounded in B UV, okay, in the norm of B, meaning that the sup of the norm of A belongs to A, is finite. Clearly, if the family A is bounded or uniformly bounded, then it is pointwise bounded. What's amazing here is that if it is pointwise bounded, then it is uniformly bounded. So proof. Let alpha belongs to R, alpha positive. Set F alpha to be set of vectors in U such that the norm of A U is less than alpha. For any A in A. In other words, F alpha is equal to U in U such that the norm, the sup of the norm of AU is less than alpha for A in the family A. So we know that the operators A are all bounded, okay? And so this is an intersection. So it's for any fixed A in A, the set of U in U such that the norm of AU is less or equal to alpha is closed. Okay, because A is bounded, therefore it is continuous, therefore this set here is closed. And F alpha, so since F alpha is an intersection of closed sets, it is closed. So this is how you get it, huh? So the operators A's are all bounded, therefore they are continuous. So since every single one of them for a fixed A is closed, therefore their intersection is closed. Next, since for every U in U, we know that pointwise it is bounded, okay? And therefore, there exists n greater than 1, a natural number, such that the sup of the norm of AU is less or equal than n. Okay? So in other words, for every U in U that exists n greater than 1, such that U belongs to Fn, which is, again, such that the sup of the norm of AU is less or equal than n. Okay, so U is the union of the Fn's n greater or equal than 1. So this is what we call an F sigma in topologies, countable union of closed sets. Huh? Keep in mind, this only finite union of closed sets is closed. And in this case, we have a countable union of closed sets, which gives us the vector space U. Now, we are going to call on bare category theorem, which is very important in these fundamental theorems. bare category theorems implies that there exists at least one such that the interior of Fn is not empty. So at least one of them has a non-empty interior. Okay, so let U0 be an interior point of Fn0. There exists epsilon 0 positive such that the ball centered, the open ball centered in U0, epsilon 0, the radius of 0, is inside Fn0. So for every U in this open ball, we have sup of the norms of AU is less than N0 when A belongs to A. So using the linear structure of the space U, we conclude that for any W in the open ball centered at 0 with radius epsilon 0, okay, we know that U plus W will be the open ball centered at U0, the radius epsilon 0, and therefore we know that the sup of the norm of A of U0 plus AW is going to be less than N0. But the norm of AW is going to be less by the triangle inequality. All this is in U, so I'm working only in the space U. Here the target set. So V. So this is less or equal than the norm of A U0 plus AW plus the norm of A U0. And this will give us, this is in V, this is less than N0, okay, plus the sup, which is finite, which is also less than N0, which is 2N0. Okay? So the sup of the norms of AW for A in the family A is bounded, uniformly bounded. And this is for every W, for any W in U, such that the norm of W is less than epsilon 0. So we are now in a unit ball, in a ball with radius center 0 and with radius epsilon 0. Now let U any vector in U. Okay? And assume first u not equal to 0, so we can divide by the norm of u. Okay, we get the u over the norm of u, okay, times del epsilon 0 over 2. The norm of this one here is epsilon 0, so it belongs to the open ball with radius epsilon 0. So this will imply that the sup of the norm of A of epsilon 0 over 2 u over norm of u is less than 2n0. So in particular, using, this is for A in A, using the linearity, we can get epsilon 0 over 2 times the norm at the bottom out, and then bring it up. So just sup will stay the same, because this is, let me write all this. This is exactly the norm of epsilon. This is the linearity. As of u, norm, okay, which is equal, since epsilon 0 over 2 norm of u, because everything is positive and independent of A, norm of AU, A in A. So, and multiplying the stuff, doing algebra, we find that sup of the norm of AU, A belongs to A, is less or equal to norm of U over epsilon 0 to n0. Okay, so in particular, so for any u in u, u not equal to 0, we have the sup of the norm of AU, A in A, is less or equal than a constant c times the norm of u. Okay, obviously this is still valid if u is equal to 0, and this will give us exactly that the norm of A for any A in A is less or equal than c, and that is exactly what we want. So here all the operators A in the family A have a norm less or equal than c, and therefore they are uniformly bounded. So this proves the theorem, and keep in mind, I insist on this, that the key ingredient in this proof is the bare category theorem. It's very important because being Banach, U is complete, and therefore we can use the bare category theorem. Okay? An application of this result, okay, a direct application, is the fundamental theorem of Banach-Steinhaus, is the fundamental theorem of Banach-Steinhaus, which was proved jointly by Banach and Steinhaus, which says, theorem, let U be a Banach space and V be a normal space. Okay? Let Fn be a sequence of bounded linear operators from U to V, which are pointwise bounded such that Fn of U is pointwise bounded, but we're going to have pointwise convergence, is convergent in V. Okay? set A, which goes from U into V, defined by the limit of the Fn. It is well defined because we assume that it converges. So it's pointwise convergence. Then A belongs to BUV. So in other words, if you have a sequence of bounded linear operators which converge pointwise bounded, so meaning that if you have pointwise conversions, you have at the end a map that is nice, meaning it is linear and bounded between U and V. So proof. So first of all, it is clear, okay, it is clear from the boundedness, uniform boundedness principle, theorem, from the uniform boundedness principle, okay, that the ANs are all uniformly bounded. Sup of the norms of the FNs is finite. So the FNs are uniformly bounded sequence of linear operators. That's step one. This is coming from next, using the properties of the continuity of the additivity and the multiplication by scalar. It is easy to see, okay, it is easy to see that A in fact is linear. Okay, so we have the linearity of the limit, so it's a linear operator, and we have the Fn's which are uniformly bounded. Next, we know from the continuity of the norm that the norm of AU is going to be the limit of the norm of Fn of U when n goes to infinity. Well, of course, we are in V here. And the norm of the Fn's of U is less or equal that sup of the norms of the Fn's times the norm of U in U, which imply that, okay, which implies that the norm of AU is less or equal than the sup of the norms of the Fn's norm of U for any U in U. So clearly, we have A is bounded and the norm of A is less or equal than the sup of the norm of the Fn's. So this is a beautiful conclusion that if you have a sequence of bounded linear operators which converges pointwise, its pointwise limit is also a bounded linear operator. So it's really interesting. The next theorem, which is the open mapping theorem, is a very beautiful theorem, very powerful theorem. So next, second, okay, theorem. Among the most fundamental ones, Banach-Steinhaus is very famous, very useful, but it's not like the open mapping theorem. Okay, so this is the open mapping theorem, and before, which was discovered by Banach himself in 1929, and before we get into it, we need some few technical lemmas. So here, so of course, as I said, this is the open mapping theorem. So first we will need some technical lemmas. Okay. Lemma 1. Let U be a normed vector space and V a Banach space. So now the target set is the Banach space. Let U be a normed vector space. Let V be a Banach space. And in fact, what in practical matters, what we do, we have a theorem, we have a proof, we look at the proof and see when did we use completeness, for example, and then we add it. This is how usually we do it. So that's why we know, for example, when do we need completeness on U and when do we need completeness on V. As we said in the previous theorem, we needed completeness on U. That's how we got bare category theorem in the uniform boundedness theorem to get the conclusion. So it depends truly on the proof that you have, and you try to make the correct assumptions that will make your proof stick. Let A be a linear operator which is onto or surjective. So in North America we use a lot onto and one-to-one, and in Europe we use a lot injective and surjective. So here you have, which means, by the way, that the range of A, which is A of U, is equal to V. Okay? Conclusion then, for any positive number R, for any R positive, there exists delta positive such that the closure, the open ball, so here I have to be very careful, okay, because it depends on the spaces, okay. So here I'm taking the open ball in V of 0 centered at 0. So the 0 here is the 0 of the vector space V with radius delta, is included in the image of the open ball at 0 with radius R, okay, in U. So this is the 0 of U, and you're looking at its image under the operator A, and you close this. So this is the closure. Okay? The proof is a little bit technical, not really complicated. It's a little bit technical. So here, let's proof. Let n be a natural number. Set Bn to be the open ball in U. We know it is obvious that U, the vector space, is the union of all the Bn's. Since A is onto, we get V, which is A of U, is the union of A of Bn for every n. Okay? So we want to use, of course, here again some kind of bare category theorems, and we need closed sets. So we know that V is complete because it's a Banach space, but the ABNs is not necessarily closed. So what we do, we know that V, because this is still included, if you take the union of A of the BNs bar closures, this one is bigger than this one, okay? And it is included in V, so we must have this equals to V. So now we have a countable family of closed sets, which gives us, covers the entire set V. So now we can use the bare category theorem again, bare category theorem, beautiful theorem, and it's amazing, implies the existence of n greater than 1 such that the set ABN ABN closer, this one has a non-empty interior. Okay, so this closed set has a non-empty interior. Let Vn be an interior point of ABN. So there exists alpha positive such that the open ball centered at Vn with radius alpha in V, this is inside A of Bn. Okay? So one has to be very careful. I mean, I may from time to time drop this index or put it depending whether you know where are we. It's the open ball, look at the center. If the center belongs to U or V, then the open ball is the open ball of U or the open ball of V. Sorry, this is closure. Okay, so now we look at the properties of Bn. So Bn is convex and symmetric. Okay, so this is known on the balls in any normal vector space. This implies so A of Bn is convex and symmetric. Okay, and by closure, because the properties of the closure and the limit, okay, will also this, okay, which these two properties still hold in the closure. So now let V belongs to the open ball centered in Vn alpha. So we know, no, sorry, let us shift it, huh? Let's shift it, let's go to 0. Because we want, the conclusion of the theorem is the balls are centered at 0, so we go to 0. Let V be a vector in 0. So we know that if you take then Vn plus minus V, okay, will belong to are in the open ball centered in Vn with radius alpha. So here, of course, we use the fact that it's symmetric. That's why whenever you have V, you have also minus V. So uh, that's why we have the property of next. So hence Vn plus minus V will belong to A of Bn bar, and since ABN is symmetric, this will imply that so minus Vn plus V, I'm sorry, not minus will also belongs to A, B, N bar, because ABN is symmetric. So now we have so we have V minus Vn and V plus Vn are all in ABN bar. Finally, if we take the convexity, by convexity, we get V, which is V minus Vn plus V plus Vn over 2. It belongs to ABN bar. Therefore, so B0 V of 0 alpha is in a Bn bar. Next, we note that in the normal linear vectors, balls, I'm not going to put the U because it's true in any normal vector. If you take the open ball centered in 0 with radius r, this is just r time the open ball centered at 0 with radius 1. So once you are armed with this, so now if you multiply, if you take the open ball centered in 0 with radius r, this will be r over n, the open ball of 0 with radius n. So in fact, what you get that from the proof, you get that from the open ball here in V, of course, 0 r over n times alpha is included in A of the ball 0 with radius r closure. So you see, once you prove it for one ball, then you can shift it, translate it. There are all these properties of the normal vector spaces which allows you to go from one ball to another or using the linear structure of the space. So this is, for every r, we found this delta such that this is the delta, okay, such that it belongs to the closure of the image of the open ball. So the proof is complete. Now we need the second lemma. Okay. Let U and V be Banach, be a Banach space. And V be a normal space. Okay. So let A be a bounded linear operator. Okay. We assume there exists epsilon such that the open ball is in A of B1. So of course, remember A is a map that goes from U into V. So this open ball is going to be in V, okay? While this ball here, B1, is going to be in U, okay? Then there exists delta positive such that the open ball of 0 delta is going to be in the image of AB1. So in other words, we move from the closure to the original set. So it's really interesting. Um, conclusion here. Proof let V be a vector in 0, open ball centered at 0 with radius epsilon. Then we know that V belongs to a B1 closure. So for because of density of AB1 into the closure, there exists U1 in B1 such that the norm of V minus AU1 is going to be less than epsilon over 2. Of course, this is the norm in V's. This is happening in V. And this implies that a v minus AU1 belongs to the open ball centered in O with epsilon over 2 in V, of course. And here we know from the assumptions on the theorem that the ball with radius epsilon, okay, is included in AB1. So again, using the properties, if I divide radius epsilon by 2, I will be in B 1/2 in the open ball centered at 0 with radius 1/2. So this will imply, which is included in A, the open ball 0 1/2 in U closure. Okay, so this will imply that V minus AU1 belongs to A, B, Z open 1/2 closure. Okay, so there exists U2 in the open ball 1/2 such that V minus A1 minus U2 in the norm in V is AU2 less than epsilon over 4. So this is of course from the density in the closure set. So by induction, we construct, okay, sequence UN in U such that number 1 the norm of UN is less than 1 over 2 to the power n in U, and V minus AU1 minus AU2 minus AUN is going to be less than epsilon over 2 to the power n. Okay, so clearly if we look at the series now of UNs, okay, then the condition on the norm, the UNs less than 1 over n, since sigma 1 over 2 to the power n is convergent, okay, we get that sigma of the norms of the UNs is convergent. Okay, since U is a Banach space, okay, it's a Banach space. We have seen in the study of vectors series that this will imply that sigma of UN is convergent in U. Okay, set the vector U, set the vector U equal the total sum of the UNs, right, from 1 to infinity. Okay, easy to prove that the norm of U is going to be less than sigma of the norm of the UNs from 1 to infinity, which is less or equal sigma of 1 over 2 to the n from 0, because U1 has a norm 1. Okay, so remember, if you look at U1, first U1 was in the norm 1, in the ball with radius 1. So here is going to be from, so if we go here, this is true. I should have maybe written this. This is true for n greater, it's minus 1 in fact, greater than 1. Okay? So in this case, this will give us from 0 to infinity, which implies that the norm of U is less or equal than 2, because the total sum will be 1 over 1 minus 1 half, and that's 1 over 1 half, and that's 2. Okay? And because of the condition norm of V minus A of U1 plus U2 plus UN less than epsilon over 2 to the n, we get that the limit, so the limit of A of U1 plus U2 plus UN is equal to V when n goes to infinity. Okay, and since A is a bounded linear operator, therefore A is continuous. So the limit of A of U1, U2, UN, and these are the partial sums. So this is the total limit A of the total sum, which is U when n goes to infinity. So this tells us by uniqueness of the limit, so A of U is equal to V. Okay, so remember, V was chosen arbitrary. Let's go back again at the beginning. V was arbitrary in the open ball centered at 0 with radius epsilon. So we get that the ball in V, the open ball 0 epsilon, is included in A of, and U has the norm less or equal than 2, so this is B2. Okay? We can take it even large. I believe the theorem is still valid if you take the closed ball instead of the open ball. And this tells us that the open ball of 0 epsilon over 2, because I'm dividing by 2, is included to the open ball, I'm sorry, the closed ball centered at 0 with radius 1. And that is exactly the theorem if we take delta to be equal to epsilon over 2. Note that this conclusion, in fact, for bound linear operators will imply that A is onto. Indeed, remark. Okay. Let A belongs to BUV and assume there exists delta positive such that the open ball 0 delta in V is included in A of the unit ball, okay, of U. This is of U. Then A is onto. Okay, indeed, okay, let indeed let V in V any vector. We know that we assume that V is not equal to 0 because 0 is in the range. So here we can assume without loss of any generality, we can assume V not equal to 0. Okay. We know that if we take V over norm of V, it has a norm 1 in V. And if I multiply by delta over 2, this will belong to the open ball in V centered at 0 with radius delta. Okay? So there exists U, okay, in U with norm of U less or equal than 1, such that A of U is equal to delta over 2 V norm of V, which implies that A times 2 over delta norm of V U is equal to V, or if you want, that V belongs to AU. So V belongs to A of U, okay, which implies that V is equal to AU. So A is onto. Note that I don't need the boundedness of A. I only need linear operators. So for any linear operator for which you have this property here, for some delta, then the linear map is onto. Okay. So now we're ready to prove the main theorem, which is the open mapping theorem. So here, theorem. So again, this is known as the open mapping theorem. Let U and V be Banach spaces. Pay attention that lemma 1 needed U to be Banach and lemma 2 needed V to be Banach. So let U, V be Banach spaces. Let A belongs to BUV, so it's a bounded linear operator. And we assume that A is onto. Assume A is onto or surjective. Okay? Okay. Then A is open map, meaning that the image of an open set is open. So keep in mind, when we take continuous functions, we saw this when we discussed the metric spaces, is the inverse The topological characterization of continuity is the inverse of an open set, not the direct image of an open set. This is not true in metric spaces. The direct image of a closed set or open set is not necessarily closed nor open. And that's why the conclusion here is truly amazing and fundamental here. Moreover, we have a little bit more to say in this theorem. Moreover, there exists alpha positive such that for any v in V in the range, there exists a u in U such that A of U is equal to V. That's because it's onto, but we have a control, and the norm of U is less or equal than alpha, the norm of V. So we have some kind of uniform control here. Proof. So let O be an open subset of U. Assume it's not empty. Okay. Let V0 belongs to A of O. So what we're going to show that V0 is an interior point. Let us prove that V0 is an interior point of A theta. Since V0 belongs to the image of O, there exists U0 in O such that A of U0 is equal to V0. And since O is open, there exists an R positive such that the open ball R is in O. Keep in mind we are in U, so it's an open ball in U. So now lemma 1 implies the existence of epsilon such that the open ball with radius 0 is in AB1 closure. Of course, the open ball of 0 and the epsilon, this is 0V, and this is the open ball in V. Okay? Since U is a Banach space, this is of course, since U is a Banach space, there exists delta so then now it's lemma 2. There exists lemma 2. There exists ep delta such that the open ball radius delta is included in A B1. So remember, it's allowed us, lemma 2 allowed us to move from the closure to the inside the image of the ball. Okay? So now using the properties of the so if we multiply by R, we get that so the image 0 R delta is going to be included in A BR, okay, where BR is U in U such that the norm of U is less or equal than R, okay. And we can take a little r prime instead of r. We can show that, in fact, we can make it a little bit strictly less in this r business, and we can prove that um, there exists delta prime less than r delta to get B open ball 0 delta prime is included in A open ball, okay, with radius r, which is included in and now what we do, we translate, so we get V0 plus the open ball 0 delta prime is included in A of U0 plus A of the open ball, which is the same as A of U0 plus B0 0R. This is the linearity of A, and this is equal to A, the open ball U0 with radius R. So this implies that the open ball centered at V0 with radius delta prime is included in A of B0 U0R. Remember, this is in V and this is in U, and we know that this is included in A of O. So what we proved is that we found a ball, an open ball, centered around V0 inside this. So V0 is an interior point of A of also A is indeed an open map. Okay, now let us prove the control. Let V in V, okay, and we can assume that V is not equal to 0 as usual. And let us take delta prime over 2 did we have delta or delta prime in here? Delta. Yeah, so let us use this here. So we can use delta over 2 times V over the norm of V. So that belongs to the open ball 0 delta. So delta over 2 norm of V, V belongs to A of the unit ball. So there exists U in B1 such that A of U equals delta over 2 norm of V, V, which implies that V is equal to A of 2 over delta norm of V, norm, I'm sorry, not norm, U, okay? So, and the norm of 2 over delta norm of V, U. So let us just clarify, because people, this is in V and this is in U, okay? So this is equal to over delta norm V in V, and the norm of U, since we are in the closed ball, this is less than 2 over delta norm of V in V. So for any V in V, there exists U in U such that A of U equals V, and the norm of U in U is less than 2 over delta times the norm of V. So this 2 over delta is indeed our alpha in the theorem. So it's a uniform control here. This proves the theorem. As an application of this beautiful theorem, there's so many, as I said, these theorems are fundamental at the core of the geometry of function analysis and the study of function analysis and normed vector spaces. But let us just see some few applications. So the first one is an equivalent norm result. So recall that if U is a normed vector space, okay, let's norm one, not a normed vector space, I'm sorry, it's just a vector space, okay, is a vector space, and let's take norm 1 and norm 2 be two norms on U. We say that these two norms, norm 1 and norm 2, are equivalent if and only if there exists alpha positive, beta positive, such that alpha norm 1 is less than norm 2 less than beta norm 1. Okay? So we have seen that before when we discussed the lecture on normed vector spaces, that in the case of finite dimensional vector spaces, all the norms are equivalent. Any norms are equivalent. So here we take theorem. Let U be a vector space. Okay. Let norm 1 and norm 2 be two norms on U such that U1, which is U with the norm 1, and U2, which is the space U with the norm 2, are Banach spaces. So these two norms are complete, are Banach spaces. So the vector space U is complete for both norms. And we assume that there is a kind of comparison between the two. So assume, for example, that norm 2 is less than norm 1. Okay? Then there exists alpha positive such that the norm 1 is less than alpha times norm 2. In other words, both norms 1 and 2 are equivalent. So it's really amazing because you don't need to have both norms. So you just need one comparison, one inequality, and you get the other inequality to get the equivalence. But what you need, very important, what you need is the completeness, the Banach structure for both norms. So the two norms should give us a Banach space on U. Proof. So let A be the operator going from u1 into u2, defined by u gives me a of u equals u. Okay? So of course the norms are different. Huh? So a, okay, the operator a is obviously linear. So it belongs to L of u1, u2. And we have the norm of a of u2 equals the norm of u2, which is less than the norm of u1 from our assumption for any u in u. Right? So this tells us that a is in fact bounded. Okay? And we know that both u1 and u2 are Banach, and a is onto-surjective. So the open mapping theorem, okay, implies that A is an open map, okay, so there exists delta positive such that the open ball with radius 0 delta, this is in the target space 2, u2, is included in the image of the open ball with radius 0, 1 in the space u1. Okay? So, or because A of the space is the same, A is just the identity, 2 in 0 delta is included in B 0, 1 of 0, 1. So meaning that if the norm of u2 is less than delta, then the norm of u1 is less than 1. Okay? Again, we have seen this. We played with the homogeneity and so on and so forth, and we get that in fact this will imply that the norm for any u in u, we will show that the norm u1 is, for example, less than 2 over delta, the norm of u2, and that's exactly what we wanted to show. Okay, so we have done this before. It's just you multiply and then you divide. You assume u is not equal to 0, and then you see that this inequality is still valid if u is equal to 0, and you get what you want. Okay, so as a corollary, we get again this is a direct consequence as a corollary. Okay, we have the following result, which we mentioned earlier. I have the following result. Corollary. Okay. Let U be a finite dimensional vector space. Okay. All norms on U are equivalent. So we have seen this and we have it proved it. It's a little bit tricky. I mean, the proof we gave before is a little bit complicated. But let's see how this proof now becomes trivial and easy from the theorem that we just proved. Okay. So first proof. Let U be the span of U1, U2, UN, where N is is the dimension of U. So it's a finite dimensional space, so you have a basis, finitely many vectors that spans the space U. So let norm here, any norm, be any norm on U. So we know that U with any norm is complete because it's just a copy of Rn. So it is complete for any norm. Okay. So it is Banach space. And now we look at for any U in U, we have the norm of U is equal to the norm of alpha 1 U1 plus alpha 2 U2 plus alpha n Un. For any vector U, you can find the linear combination of the Ui's in a unique fashion. Alpha 1, alpha 2, alpha n are unique. This is less or equal to sigma of alpha I norm of Ui's, I from 1 to n. Okay. And since I have finitely many vectors, this is less or equal than a constant, which is the max of the norms of the Ui's, sigma of absolute value of alpha i's, n. Okay. Next, you see that the quantity, let's call it norm 1 of U equals sigma of absolute value of alpha i's. This is a norm, so a norm on U, okay, for which U is complete anyway, because it's complete for any norm. So what we have is that, so norm of U is less than the norm of U1 for any U in U. I'm sorry, there's a constant C, where C is the max of the norm of the Ui's. So now we see that the theorem, the previous theorem, okay, the previous theorem implies that our norm and norm 1 are equivalent. So you see, we found generic norm 1, and all the norms are equivalent to it, and therefore all the norms are equivalent, because clearly if norm 1 is equivalent to norm 2 and norm 2 is equivalent to norm 3, then norm 1 is equivalent to norm 3. Next, we discuss another beautiful theorem. So the third fundamental theorem, which is known as the closed graph theorem. And before we go in, let's recall some stuff. Let U and V be normed vector spaces. Let A be a linear operator from U to V. So we define the graph of A to be U AU with U in U, and clearly the graph of A is a subset of U cross V. Okay, so first, okay, U cross V is a vector space, and if U and V are normal spaces, then the quantity of U comma V equal norm of U in U plus the norm of V in V defines a norm on U cross V. And if U and V are Banach spaces, then U cross V with this norm is also a Banach space. Okay, so this is the product of two normal vector spaces, and everything is preserved. So clearly, the graph of A, since A is linear, is a subspace of U cross V. Okay, and finally, if A is bounded, okay, therefore A is continuous. We just need continuous, in fact. Then the graph of A is closed in U cross V. Okay? Indeed, assume that UN converge to UV, and we want to show that UV belongs to the graph, okay? Because UN converge to the graph as n goes to infinity. So by definition of the norm in the product, we get that UN converge to U as n goes to infinity in U, okay? Since before that, and A of UN converge to V in V. Okay, so now since A is continuous, A of UN also converge to A's of U when n goes to infinity, and finally the uniqueness of the limit gives A of U equal to V, so the limit UV belongs to the graph of A. So if A is continuous, the graph is closed, no doubt. Okay? The converse is not clear. Okay, and that is the theorem here, theorem. The closed graph theorem. So it says, let U and V be Banach spaces. Let A, because we want to show that it's bounded and it's continuous, so that's why we just start with a linear operator, UV. Assume the graph of A is closed in U cross V, then A is bounded. That is, A is continuous. This is a typical result that's known only in the vector spaces, in normal vector spaces. There is no extension of this to metric spaces. Proof. Let A belong to LUV such that the graph of A is closed in U cross V. So now define the new norm, set norm of U sub A to be the norm of U, the original one, in U, plus the norm of AU in V. In other words, this is the norm of U, AU in the product. Okay? Space. So we have the norm of U, original one, is less than the norm of U, the new one. Okay? Note that it is a norm because A is linear. So this is a norm, and moreover, what's amazing is that U with this new norm is a Banach space. And the reason why, okay, is a Banach space is because the graph is closed. Indeed, if UN is Cauchy for the new norm, then UN is Cauchy for the norm, the original one, and AUN is Cauchy in V. Since we assume that both U and V are Banach, since U and V are assumed to be Banach spaces, then limit of UN equals to U when n goes to infinity belongs to U, and limit of AUN when n goes to infinity equals to V in V exists. Okay? Since UN AUN belongs to the graph of A, we must have UV belongs to the graph. Okay? In other words, we have V equals to A of U. Okay? A of U so U sequence UN converges to U in the sense of the new norm of the new norm A. So the new norm infers the structure of a Banach space on U, and therefore, because we said that the norm of U is less or equal to the norm of A, so there exists alpha such that the norm A is less or equal than alpha, the norm of U for any U in U, the original one. So they are equivalent for any U in U. Okay? Okay. Since the norm of AU in U is less or equal than the norm of U in A, we get that the norm of AU, I'm sorry, not in U, this is in V. And V is less or equal than alpha norm of U in U for any U, for any U in U. So of course this tells us that A is a bounded linear operator, therefore A is a continuous linear operator. This completes the proof of this theorem, and this is almost the last one besides the Banach theorem, which we'll see in a different lecture. This gives us all the fundamental theorems that will be at the core of studying the structure and the properties of normal vector spaces. Thank you very much for your attention.